Hey, what is up? Asile here from InstaProofs, and in this video, I'm going to go over the quadratic formula. Now, the quadratic formula is pretty much the anchor to all of algebra involving factoring, solving, expanding, rearranging, and many other operations on second-degree polynomials, or quadratic functions. Therefore, knowing its origins is quite vital, because if you just know the quadratic formula solely as plug and chug, then everything else involving quadratic functions will never really make much sense. But if you can learn to derive and play around with this formula, then all of it will make sense. Because believe me, deriving this formula is as hard as you can get. And if you can master the hard stuff, then the easier or medium stuff should become a sixth sense. So given a second degree polynomial ax squared plus bx plus c, where a, b, and c are constants, and a can never be 0, we want to derive the formula that solves for x when f of x equals 0, or the x-intercept. In other words, we want to derive the quadratic formula. And we want to provide a graphical interpretation for different cases of this formula. So we start off with our quadratic function, and we set it equal to 0. From here, we ask ourselves, what is our end goal? And what is the very first step from here that can get us there? Well, our end goal is isolating x, and the only way we can even isolate x is to have it appear in one place in the equation. However, x is at two places in this formula, next to a as x squared, and also next to b as x. So how do we put it in one place? The answer to this is a method called completing the square. The exact logic behind this method I will leave for a different video, but for now I just want you to follow through the process. So we factor out an a, and now we have a times the quantity, x squared plus b over a times x, plus c on the outside. Now this is where the logic comes up. In order to get x in one place, we have to put the expression x squared plus b over a x in the form x plus h squared. And the way we do that is by realizing that x plus h squared by FOILing gives x squared plus 2hx plus h squared. And here we equate x squared plus 2hx with x squared plus b over ax, and let 2h equals b over a. All we have to do now is to get to the form x plus h squared is to introduce an h squared. We do that by adding an h squared and then subtracting one next to the x squared plus b over ax term. Then we take out the unnecessary negative h squared out of the expression by distributing an a to it. Now that we have x squared plus 2hx plus h squared, we can simply replace it with x plus h squared. And seeing that b over a equals 2h, h must equal b over 2a, while h squared must equal b squared over 4a squared. So we plug in for h and h squared and get the following. We then multiply c by 4a over 4a to get common denominator of 4a with the only other term outside the square expression, and merge both the terms into one. By doing so, we have 4ac minus b squared over 4a added on the outside. We minus this term on both sides, and by distributing the negative, we get b squared minus 4ac all over 4a equal to a times the quantity, x plus b over 2a squared. Now we divide a on both sides and get an a squared on the denominator for the left side. From here, we know that if an expression x is squared and set equal to another expression y, then the expression y equals the plus or minus of the radical of the expression x. By the way, this x is not to confuse with the x we are trying to solve. I apologize for that confusion. So by applying this rule and seeing that our x expression is x plus b over 2a, while our y expression is b squared minus 4ac all over 4a squared, we get the following. And taking into account the property that the radical of a function f over a function g is equal to the radical of f over a radical of g, where in this case f is b squared minus 4ac and g is 4a squared, and further realizing that the radical of 4a squared is simply just 2a, we then get this. Now all we have left to do is to minus b over 2a from both sides, and seeing that both sides have a common denominator of 2a, we nicely get our answer of x equal negative b plus or minus the square root of b squared minus 4ac all over 2a. And this here is a quadratic formula. So there you have it, the derivation that pretty much every algebra student complains about, and rightfully so. Now I know most of those complaining students will also brush this off as unnecessary. But believe me, when I said hardest, this is the hardest you can get with quadratic functions. I mean, we utilize foiling, radical laws, completing the square, and even factoring. You have all these concepts that you're taught munched up into one process. Instead of brushing it off as unnecessary, I thought, why not benefit from learning it? I mean, you really have nothing to lose. So on to the graphical interpretation. In the quadratic formula, if the term b squared is greater than 4ac, then it follows that the expression b squared minus 4ac in the radical is always positive. This in turn implies that there can be two real solutions for x, because since the expression is positive, the radical of that positive expression is also positive. And since we have plus or minus a radical giving two possible radicals, then we can only have two real solutions. And in the graph of this, the vertex of the parabola is below the x-axis, and we have two x-intercepts. Second, if b squared equals 4ac, then b squared minus 4ac inside the radical must equal 0, so the radical must also equal 0. This implies that there can only be one real solution, because in the formula we have a negative b plus or minus the radical expression all over 2a, and since the radical is 0, the formula reduces to x equal negative b over 2a, being however only one solution. In the graph, the vertex is right at the x-axis, and we have exactly one x-intercept, which is the vertex. And just as a check, you know that the x-coordinate of the vertex of a parabola is always negative b over 2a. And note also that the x-intercept here is negative b over 2a, implying that the x-intercept is our vertex, consistent with our graph. Lastly, if b squared is less than 4ac, then the expression b squared minus 4ac inside the radical is negative. Since the radical of a negative expression yields an imaginary term, where we get imaginary number I times the radical of the absolute value of that negative expression. And again, since we have either plus or either minus that imaginary radical, then we get two imaginary solutions and zero real solutions. In the graph, the vertex is right above the x-axis, and we have no x-intercept, or no real solution. So yeah, there you have it, the derivation and a graphical interpretation for the quadratic function. I really hope this video comes up with a great benefit. Until next time, thanks for watching.